welcome everyone to today's edition of the Wilson Science and Technology Forum. Uh, you know, Part of my goals, two of my major goals for this forum are number one, to provide a platform that allows the general public to understand the evolution of technology that impacts their lives, number one. And secondly, my another major goal is to engage the younger generation in this conversation. Today, we have a speaker who addresses both of those goals. Dahlia Saba is a second-year graduate student at the University of Wisconsin. She is studying as part of her research project, her thesis work. She's studying the evolution of the electric grid and changes in the grid. And so it accomplishes both, Dahlia, to have you here today as a member of the next generation. We're looking forward to your help in making sure that the things that happen in the future benefit all of us. So, not to put any pressure on you, kid, but you're an important part of the future of this nation and the planet. And so we're just delighted to have you speak with us today. And finally, I want to say it's important to acknowledge that Dahlia is the granddaughter of Don and Lita Nelsen, longtime members of our crew. We're
Mhm.
especially happy to have the Nelsons with us today as well. So, Dahlia, let me turn the floor over to you and welcome to the Wilson Forum.
Thank you so much, Ron, for the very kind introduction. No pressure on saving the world or anything like that. But yeah, so I'm a second year PhD student at the University of Wisconsin-Madison. And let me see if I can share my presentation.
Yeah.
Let's see.
There we go.
Can you see it?
Yeah.
It worked.
Great. So hello. As I said before, yeah, I'm a second year PhD student studying the electric grid. And so I'm gonna kind of spend part of my talk talking about my path towards deciding to do a PhD in power systems and to work on the electric grid. And then I'll talk a bit about some of the challenges facing the electric grid today with the integration of renewable energy. Hopefully, I will tell you about some challenges that you may not have thought about when it comes to integrating renewable energy onto the grid. So, a bit about me. I'm from Oakland, California. I got my bachelor's in electrical engineering and computer science from UC Berkeley in 2023. Um, I then started a PhD program at the University of Wisconsin-Madison. Along the way, I earned my master's degree last fall. And I'm also pursuing a certificate in energy analysis and policy. And so hopefully I hear that a lot of you are interested in the policy side of things or the kind of more practical side. So hopefully I can answer those questions to some extent, although many of those questions nobody can answer. But
Mhm.
um, yeah, and my research interests are about integrating renewable energy into the power grid dynamics, which I think is kind of a very abstract phrase, but I will talk about that in a bit more detail later. So hopefully that becomes a little bit more clear what I mean by that. And also hybrid AC/DC grids, which I won't talk about as much in this presentation, but I'm happy to answer questions about if that's something people are interested in. All right. So first, I'm going to kind of go over my path to starting a PhD. So I'm going to start in 2019 when I started my undergrad at UC Berkeley. I started in electrical engineering and computer science, um, which I decided to do because I had done some coding in high school. I thought this is pretty cool. Everybody's talking about computer science. Everybody's talking about coding. The big hot new thing. I guess it wasn't even that new at that point in time. But I didn't really know what I wanted to do. I just thought it was cool. And then it's also, I guess, important to know because I grew up in the Bay Area, in at that point in 2017 and 2018, since then there have been more, but there had been very large wildfires involving the electric grid. Several of them had been started by the electric grid. Many of them contributed to blackouts. Um, And this was very noticeable because the entire Bay Area was filled with smoke. We had school canceled. We couldn't go outside. We had to wear masks before that was a thing that people did regularly. Um, and so it was very noticeable, and very apocalyptic to see the sky filled with smoke and the sun be kind of blacked out a little bit. So that was kind of on my mind, but wasn't really on my mind as something that I could do anything about, or was relevant to me other than it sucked. Um, but yeah, I guess also in 2019, after I started, I should mention there was a very large scale public safety power shutoff in the Bay Area that affected millions of people, including me and my parents. Um, and basically, what this was there was a very high risk of wildfire that day. And so PG&E decided that the best course of option was to shut off the power and intentionally cause targeted blackouts to avoid high winds causing a power line to break and start a wildfire. And it's very unpopular to have your power cut off, if that is not obvious. However, they also have had a lot of statistics or estimates of like thousands of potential ignitions that were prevented by shutting off the power. And so there are some very kind of thorny topics involving the power grid and climate change that come up, both about the when you talk about decarbonization, but also when you talk about the resilience of the power grid in the face of changing climate conditions. Um, so all of that to say, in 2021, I decided I was still kind of figuring out what do I want to do with computer science? Is there any application here that I find motivating and meaningful? And then I decided to apply to an internship or an internship program that specifically was looking at internships in energy. And I saw that there was a company working on the power grid, specifically on data analysis for data measured from the power grid. And that company was Ping Things. Um, so because of that, with the power grid on my mind, I thought, okay, that sounds pretty cool. I understand why this is important. Oh, sorry, let me go back. And so I decided to apply for that internship. Through that, I learned a lot about how the power grid works, which I previously had no idea about. Um, and I decided, instead of just doing this data analysis stuff, what if I actually start working on the power grid itself? And so through that internship, I got connected with a professor, Professor Alexandra von Meyer at Berkeley, and I started doing research with her. Um, and so the first project I worked on is called harmonic phasor research. This is, I guess, for the signal processing people in the audience, maybe more interesting. Um, but basically, at a high level, we have an AC power grid. That means that we have, in theory, all of our voltages and currents on our power grid are perfect sine waves. Um, However, as you can see from this graph, we see, okay, the blue is the actual measured data for the current and the voltage on the power grid. And the orange is how we would approximate it as a sine wave. Um, if you can see, these do not match. This is specifically data that was measured from a house in Ireland. Um, and so this is kind of like the household distribution level power grid data. We see that there's a lot of distortion, particularly in the current. This comes from a couple things. The main thing is that the types of loads we have these days, and by load, I mean just anything that consumes power from the grid. Um, the types of loads we have today are pretty different than the types of loads we had before. And specifically, that's in the rise of what we call power electronic loads. And so power electronics I'll talk about this in more detail later, but they're power converters that convert between AC power and DC power. And we have much more devices that we use today that run on DC power. So, for example, if you have, I guess we are all on computers of some sort right now. Our computers all use DC power to charge their batteries. And so that's why whenever you plug in your computer, there's that little block at the end of your charger. And that block is the converter that converts between AC power and DC power. However, in the process of converting between those two things, your charger is not drawing power in a sinusoidal way. It is drawing power whenever it needs to in order to create a DC output for your computer. And so that basically messes up all of the like beautiful sinusoidal waves of the grid. And so that's why we see this kind of distortion in our current waveform and our voltage waveform. Um, and so in this project, I was working on how can we better approximate these voltage and current waveforms, um, and how can we better understand what's happening, either so that we can better filter out these, well, I should say, those extra bits that are being drawn that make it look non-sinusoidal. We call that harmonic distortion. And by harmonic, we mean there are these higher frequency components of these waveforms than this kind of slow moving AC, beautiful, perfect sine wave. And so this harmonic distortion could be used to either identify what loads are on the grid, or it could also be used to better have a better understanding of our power analysis, like to better be able to do analysis of what's actually happening on the grid. So what I worked on is how can we better approximate these higher order harmonic components. And so as you see in these visualizations, what I worked on is estimating these other components so we get a better match between the real value and the total analysis that we're doing. And so as you see, the voltage, it's easy to get a good match with a relatively few amount of harmonics because it's not as distorted. The current, even here, we're getting up to like 40, 50, I think it gets up to the 59th harmonic. And it definitely looks much closer than it was before, but you can still see like a gap between the blue and the orange, just based on the amount of distortion that we have here. All right. So after that project, I worked on that project for about a year. I worked on a project with the Lawrence Berkeley National Lab called Grid Sweep. Um, and so this project is also looking at the distribution grid. Um, a colleague of mine, Alex McEachern, built this device called the Grid Sweep instrument. And the idea with the Grid Sweep project is that can we understand potential instabilities on the grid by actively probing the grid and trying to find any potential oscillations? So when I talk about oscillations on the grid, this is an oscillation is essentially where you have power shifting back and forth across the grid. In general, when we want to operate the grid, the best thing to do is we put power into the grid. The power travels straight from where we put it into the grid to where we want it to go, and then it's used up. That is the ideal case. However, when we have a potential instability, that means that sometimes we put power into the grid, and instead of going where it's supposed to go, it starts sloshing back and forth between different places. Um, and if that oscillation is not damped out, it doesn't go away, then it's, first of all, it's causing losses because you have all of this stuff moving across these lines. But also, if it doesn't get damped out, then it could grow bigger. And then all of a sudden you have components start to shut off and then you get blackouts. So that's bad. Um, but the idea with this project is, can we understand these oscillations on the distribution grid without causing a giant oscillation to occur and causing a blackout? Instead, what if we just kind of poke it with a little small disturbance? Specifically, we were looking at a 1 kilowatt disturbance, which is about the equivalent of a microwave. Um, so if we do a small disturbance on the grid and we have our load create a little oscillation, it's going to change its load by a specific frequency. Can we measure that same oscillation elsewhere on the grid to understand, okay, is that frequency of oscillation susceptible to traveling back and forth across the grid? So with this project, we had I don't know if you, I guess this is a little bit small font, but you can see here um, in this section, let's see, we have three grid sweep instruments plugged into the grid that are all probing. So we have three of them because there are three phases of power on the grid. And so we're probing each of these three phases. Um, and then elsewhere on the grid, we have the same device, but turned into a different mode called the receiver mode. And basically, the reason that this device is very cool is that it has a super high precision. Specifically for the signal processing people, it had a precision in the order of parts per billion. It could pick up signal, like for the signal to noise ratio. And so this means we could get very high precision measurements and measure our oscillations hopefully far away on the grid without just getting totally drowned out by the noise on the grid. And so I worked on analyzing this data to see if we could find these oscillations. In the course of my work on the project, we weren't able to necessarily identify a single kind of smoking gun frequency instability. But what we did notice is that in one of these experiments we were doing, there was a solar panel on the roof of one of the buildings. And what we found is that you can actually, even without having a device probing on the grid, you could measure with this device the impact of the solar panel being on or off, because there were
Hmm.
certain frequencies that were injected into the grid by the power converter attached to the solar panel. And so you could actually, when the operator, I think this was at Idaho Power, the operator there did an experiment where every hour he would turn on or off the solar panel, and you could see exactly in the data which minute he turned it on or turned it off, which was pretty cool. All right. And so basically, after working on these two projects, and also through gaining a better understanding of the power grid, um, I saw that like this is a field where there is a lot of real open questions. We have we know that it's very urgent that we transition to net zero power or net zero energy systems as soon as possible. Um, and that's a very ambitious project. We have started deploying renewable energy onto the grid, but as I'll talk about later, we are still not at the point where we are prepared to rely entirely on renewable energy. But it's imperative that we figure that out. Um, so, or at least rely in very large part on renewable energy. Um, so in order, basically, I was inspired to continue doing work on the electric grid, and having enjoyed my research experiences, I decided to pursue a PhD in electric power systems. Um, so I started working at UW-Madison with my advisor, Professor Dominic Gross. Um, and yeah, I'll talk a bit about my work that I'm working on now, but I think first I just want to talk a bit about some general challenges with adding renewables to the electric grid, and talk about an overview of how the grid works today so that we can understand a bit better what the problems are when we start adding renewable energy.
This is D.
Um, so, uh, First, just a kind of overview of the parts of the grid. Um, there are So we have the power plant, which generates energy. This is a traditional view of how the grid works. We have a big power plant that's generating electricity. And then we also have um, transformers. So the transformer takes the power from these big power plants. It steps it up to a high voltage so that we can transmit it over far distances without many losses. And those are these big transmission lines that, you see on the highway. These are the ones where you can see them from an airplane because they'll have to cut down trees all around them so no fires start. Um, and then you'll have another transformer that steps the voltage down at a substation. For people who don't know what a substation is, if you ever see a fenced off area in your neighborhood with lots of crazy looking devices where you have big transmission lines coming in and all of these switches and stuff that looks scary, that's a substation. And so your substation will step it down to a low voltage so it is safe to bring the power to your houses. So all of the work I was looking at before were on these distribution systems, kind of low voltage that goes straight to your house. But what I'm going to be talking about next will be generally more focused on our transmission systems, which is kind of big, large scale, looking at how do we get large scale power to demand. So some general challenges from renewable energy. Um, this is definitely not an exhaustive list. This is just kind of some three things that might be just kind of a high level overview. Um, the first thing is, I think the thing that everybody thinks about when they think about why is it hard to rely on renewable energy for electricity. And that is that the generation is intermittent. We do not have any control over when the sun shines or when the wind blows. Um, and that's an issue because generally the way the power system works is that you generate power exactly when you need it, and you take power from the grid and you assume someone's generating it somewhere at that moment in time. However, let's say that you want to get power, I don't know, you want to turn on the light at midnight. The sun's not going to be shining at midnight, and you have no guarantee that the wind is going to be blowing at midnight. Um, and so to account for this, there are two options really in order to account for the intermittency of renewable energy. The first is to add storage to the grid. So generally, there's multiple types of storage. Generally, for this, that's either going to be hydro storage, which basically just means you pump water up a hill when you have lots of energy, and then you let it go back down the hill when you need more energy. And that's the oldest form of energy storage that we have on the grid. The issue with that is that there are very limited places where you can, like geographically speaking, that are appropriate for building hydropower or hydro storage. The second way that we have, I guess there's actually three ways. The second way that we can address this is by building more transmission. And so the idea with this is that, okay, maybe the sun's not shining here in Wisconsin, or the wind's not blowing here in Wisconsin, but maybe the wind is blowing in Massachusetts. And so if we have, or maybe the wind is blowing in California even. And so if we have larger scale transmission, especially direct current transmission is easier to go further distances. If we have more transmission lines, then maybe we can kind of account for the variability in generation and average it out a bit more so we have a higher baseline. Of course, it's very hard to build transmission lines in this country, so that I would say is a bit optimistic, but in theory, that is a good option. The third option is to, oh, and I forgot to mention for storage, of course, the other big thing is batteries. And that's the newest thing that we see with storage is people building batteries. The issue with batteries, of course, is that there are a lot of materials concerns, both in terms of the human rights issues with sourcing these materials, geopolitical issues with sourcing these materials, but also the environmental impact of these materials. All right, the third way to respond to intermittent generation is to be able to control when demand happens. In general, we actually have a very good ways of predicting how much the demand is going to be at any given moment in time. But the issue is that people like to plug in their devices whenever they want and get power whenever they need it, and don't want to try to change that behavior to help the grid. So some people have discussed the potential for demand side response. Can we control when people turn on their power to make it match when there is generation? Of course, there's lots of issues with popularity of that. To what extent do people have control over that, etc. So that's an open area of research. All right. So the second potential issue with renewable energy, this is specific to distributed renewable energy. So when I say that, I mean renewable energy that instead of being generated on the bulk power system, on the transmission system, is generated on the distribution system at like the household level. And generally, when we talk about this, we mean renewable rooftop solar. The issue with this is that historically, we have made assumptions in all of the analysis that we do on the distribution grid or most of the analysis, that power flows from the substation, from our bulk power system, down to the household, and that it only flows in that direction. And there's a lot of analysis and a lot of, like, for example, sizing the distribution lines and figuring out how much power we expect to go on a different line that depends on that assumption of one-way power flow. And so now that we are changing that because we have solar panels on people's rooftops sending power back the other way, some of those assumptions are being violated. And so that is increasing the need for kind of new forms of analysis for distribution grids. The third one, which is going to be the one that I'm going to spend the most time about because this is what I work on, is the dynamics of the grid. And so basically, when I talk about dynamics, I mean, how does the grid change in response to small disturbances happening? Because we constantly have fluctuations on the grid. This could be in response to a major event, just of, oh, like, a generator went down and all of a sudden we have a huge imbalance in supply and demand, or it could be just small fluctuations. How does the grid able to respond to small fluctuations in demand? And as I'll talk about, we have a historical version of responding to this that is based on the presence of large synchronous generators, like the types that you have for coal, natural gas, nuclear energy, but that you do not have for renewable energy, specifically for wind and solar power. All right. So first, let's just talk about how does the grid historically respond to changes? And so in order to do that, I'm going to talk a little bit about how synchronous generators work. So basically, the way a synchronous generator works, we see on the left here, we have a magnet, which has a north and a south pole, that spins around. And that magnet, as you can see on the right, this is like a giant machine. This is on the right, I think this is about a 60 megawatt hydro turbine. Actually, this one might be 30 megawatts because I think there's two of them at this plant. So this is a relatively on the smaller side of a generator, but that's taller than I am. And I'm not a very short person. So these are very big devices. And what you have is a magnetic rotor. So a magnet, either an electromagnet or a permanent magnet, spinning around. And around it, you have these loops of wire. And so our electromagnetic laws, which, seem a little bit like magic, but basically what Faraday's law and Lenz's law and all of these things tell us is that when you have a magnet, a changing magnetic field, inside of a loop of wire, that will induce a changing voltage, in that wire. And so essentially, as this magnet spins around, because it's spinning at essentially a constant frequency in theory, that will create a sinusoidal voltage of a constant frequency in each of those loops of wire around our spinning rotor. And those loops of wire are attached directly to the grid. And so that creates our sinusoidal AC voltage on our grid. And what's important is also that the speed of, or the frequency of that sinusoidal voltage is directly proportional to the physical speed of that rotor. Another thing that I want to mention is that the voltage frequency of that rotor will always be synchronized. And so the voltage everywhere, the frequency everywhere on the grid, at least in our steady state, should be exactly the same. And that just ensures that we can actually transmit power from place to place and that power doesn't just slosh back and forth and not actually get used up. All right, so let's look a bit at how does the grid match supply and demand in a system that depends on synchronous generators. So this is a diagram of the response of the generation to a disturbance. So one thing that's important to mention, which is just kind of seems impossible and unfathomable, is that the power supplied by generation needs to exactly match at every point in time the electricity being consumed from the grid. And that is in every single instant in time. We need to have, I'm ignoring energy storage for now. But we need to have an exact match between the amount of energy supplied and the amount of energy taken out of the grid. And so, you can imagine like the amount of energy taken out of the grid is changing by small amounts at every point in time. And we have good approximations, but it's not going to be 100% perfect to know when someone plugs in their laptop exactly at which instant they're going to do that, or when someone turns on their microwave. And so we have all of these control systems embedded in our generation that allows it to account for these small changes in current and or in load. So if we look at this there are kind of two ways that we account for this in the short term. Long term, that's a different story. The first is, let's say, okay, I'm going to microwave some soup for lunch. At the instant that I turn on my microwave, that's about 1 kilowatt of load that is added to the grid. And you might ask, like, okay, where does that come from? Because nobody knew I was going to turn on my microwave at exactly that instant. The answer is that additional power comes from the physical rotational kinetic energy of our synchronous machines. And so in that instant, those machines will slow down slightly because of the fact that I'm taking energy from their kinetic energy. And so as those machines slow down, we see on this graph of the frequency of the entire grid will start to drop because everything is slowing down slightly. Now, that is called our inertial response because it is the physical inertia of these rotating masses that determines how fast that frequency drops. Then we see that, okay, we have these sensors on our generators. This is called a turbine governor system. These are mechanical systems that detect if the rotor is slowing down. And in response, they will start injecting more power from the mechanical generation. So that might be like, for example, rerouting more steam from your coal-fired power plant into our turbine to make it spin a bit faster. And so that first is slowing down. That's this inertial response here. And then that secondary part where these automatic control systems kick in, that's called our primary response. And that'll kind of stabilize our frequency and prevent it from dropping super low. Then later you'll have some other outer control systems that essentially redispatch our power plants to get our frequency back up to 60 hertz. So that's how, in general, in the legacy system, we respond to disturbances. However, let's look at how renewables work. Specifically, hydro works very similar to these synchronous generators. Hydro uses synchronous generators, so hydro isn't an issue here. But for wind and solar, the most rapidly growing forms of renewable energy, let's see, they work fundamentally differently. And so the main difference here is that they interface to the grid through power electronic converters. So as I mentioned before, these converters allow us to transfer power between AC power and DC power. For solar, the reason that we need this is that solar panels generate DC power. The way that they work is that you have this kind of silicon piece of panel. The light hits the panel and causes all of the electrons to move in one direction. And because you have current that's moving constantly in one direction, that creates DC power. And so in order to get it into AC power to make it compatible with the grid, we need to use a converter. For wind power, I would say it's a little bit less intuitive because the wind machine is connected to a synchronous generator of some sort because you have the spinning turbine that then creates a spinning AC wave. The issue is that the wind does not blow at a constant speed.
I wonder if this is who that is, probably.
And so the wind does not move at a constant speed. And so in order to ensure that we get a kind of beautiful constant frequency sine wave that we put into the grid, the way that often we do it is by converting that AC power, the messy AC wave that comes from the changing wind speed. We convert it into DC power and then we convert it back into a nice AC power. There are other ways people do this in the US. There's some that are more complicated, but I'm just going to stick to this one for now. And so what you can see here is that in the solar case, there's no spinning inertia. There's no rotor that's spinning around. So we don't have any inertia in the solar case. In the wind case, we also, there is the inertia of the physical wind turbine, but because we're converting it to DC power first and then converting it to AC power, we're losing that link between the AC frequency that we put on the grid and the physical inertia of the wind turbine. Um, so all of that kind of also begs the question of how do we control these converters? How do we know what frequency we should put on the grid, how big the voltage that we put on the grid should be in order to make our whole system stable and able to respond to disturbances? So there are really two paradigms for how do we control converters. There's the grid following control and the grid forming control. So the grid following control is used for basically all types of renewable energy that are currently on the grid today. The idea with grid following control is let us see if let's say I'm a solar panel or whatever, I'm a converter for a solar panel, and I want to put I want to put solar power onto the grid. The idea with grid following control is let's just see what the grid is already doing, and try to replicate that, try to put out an AC voltage and frequency that is matching what is already happening on the grid, and try to put as much renewable power as I can onto the AC grid. The reason people do that is that's like kind of simpler, and it maximizes the amount of power. However, the problem with that is that it assumes someone is stabilizing the voltage on the grid. And that's all fine and well if you just have a few solar panels here and there and you still rely primarily on fossil fuels. But if we are trying to transition to a system that relies on renewable energy, we need to make sure that our renewable energy is able to stabilize the grid and doesn't just assume that someone else is doing it. So that's the idea behind grid forming control. Grid forming control is an area of active research. It's not as widely deployed, although there are places, specifically Kauai actually has like a system that relies primarily on renewable energy, so they have grid forming control. But the idea here is how can we pick our voltage and our voltage output onto the AC grid to help stabilize the AC grid, and help it out and help create that stable waveform that we can all use to follow. So yeah, that's the idea behind grid forming control. So now, of course, then the question is, well, I talked before about how the physical inertia of the system is what slows down that frequency drop. And then I also said that these renewable energies, they don't really have inertia. So that leads to another problem of, wait, how do we prevent the frequency from just dropping super fast and the whole system crashes if there's a disturbance? And so that goes to when I talk about the fundamentally different dynamics of renewable energy, because these renewable converters, they don't have that huge amount of stored energy in the physical giant spinning rotor. However, even though they have much less stored energy, they are able to respond to events much more quickly. Because the thing about the inertia is, yes, it stores a lot of energy, but it's also physically slowing down the speed at which your generator can respond to a disturbance. Because if you imagine a giant spinning turbine, it's not going to be able to speed up instantaneously or slow down instantaneously. And so the idea with converters is, what if we can leverage the fact that they can respond more quickly to an event to say, okay, sure, if there's an event, the frequency is going to drop much more quickly, but we can also change its output more quickly. And we might get a response that looks more like this instead. And so we end up being, we could theoretically maintain the same max or minimum frequency point, which is really what causes instability. So we can still prevent the frequency from dropping too low, even though it's dropping much more quickly. And that's because we can respond much more quickly with converters. And so, yeah. So for my current research, basically what I'm working on is how can we figure out how do we control these converters? Can we develop rules that say, okay, If we have all of these different converters connected to a grid, can I come up with rules that if everybody follows these rules with how they control their converters, the whole grid will be stable? Um, and so that has to also account for the fact that we still are going to have synchronous generators on the grid, the same grid where we have these converters. It also needs to make sure that these control schemes aren't fighting each other or interacting with each other in ways that might cause these unstable oscillations. Um, the other difficult part is that a lot of, current work that does this basically says, okay, well, what if we just know all of the devices that are on the system? We know the whole system network. What if we just like numerically compute this for every system that we want to analyze? The problem with this is that these systems are massive. For example, the Eastern Interconnect of the United States goes all the way from the center of the United States to the entire eastern half, excluding Texas because of Texas. Um, that's, huge amounts of individual devices that are on this grid. And so it's simply not feasible to try to compute the way that these things will interact each other at such a large scale. It would take forever to run, especially if, maybe you start switching lines so that to change the system topology, then all of a sudden you have to just recompute everything. So instead, I'm working on developing more analytical, decentralized conditions. So you could have a rule that just applies to each converter on its own and requires not so much detailed knowledge of like every single line on the system. Finally, I didn't really talk about this as much in this presentation, but we also need to make sure, I've been talking about the AC side of the converter, making sure that the AC grid is stable. But the converter also has a DC side, and there's a DC voltage that's connected to your generation. This also is relevant for DC transmission. So we need to make sure that not only is our AC side stable, but also that we're not pulling so much power out of the DC side that will just, make our DC voltage crash to zero, and that'll also destabilize the system. So the thing with these converters is we have to analyze both sides. And so that's the other part that I'm looking at in my research. All right, so I'm going to end my presentation there. I'm very happy to answer any questions that people have, either about what I've talked about here or I'll do my best to answer other questions about the power grid if people have them. But yeah.
Well, Dahlia, I want to thank you for that perspective on the grid. You mentioned a number of things that to me were new and I hadn't understood. For example, I did not realize. I guess I should have thought it would be the case, but I didn't realize that grid forming, I guess it is, converters are now really the research that needs to be done is on grid forming, isn't it? Or is it? Am I
Yeah,
getting?
I think the
In
other
order to use renewables, you've got to deal with that problem.
Yeah, exactly. And I think that like there has been lots of work done on this. I think for like, 20 years or so, people have been working on this. Part of the other issue though is from a utility perspective.
Yeah,
They don't want to put a new technology onto their grid if they don't know how it's going to interact with other things.
right, right.
Because the thing with grid following control is it's kind of it works because we just don't have that much of it, and it's not, as long as it's not disturbing things too much and we have enough synchronous generators that they can make sure the grid is stable, then it's not really a problem. But the issue is we don't know what that tipping point is of how many grid following controlled renewable energy sources does it take to destabilize the system? Because there's no way of figuring out, okay, if we have 20%, are we fine? If we have 40%, are we fine? Or if we have
Yeah,
60%, are we fine? Nobody knows, and it actually depends a lot on the system. Um, and system to system. So you have some places where you have 50% renewable energy and there's no problems, with this grid following control. And some places where you start noticing problems at like 30, 40%. Um, so
right. So
yeah.
when you're dealing with this problem, when you've got renewables that have that are going to become a part of our life and increasingly so. So what is the research you're doing in terms of grid forming uh, converters? I mean, are there new materials involved? Is it a systems problem? Is it Is it an electronics issue? What are the particulars?
So it's really, so I don't work so much on the like physical electronic side of things.
Yeah,
But this is really just a problem of control of how do you like it's the same device. I mean, you might have different components in there, but it's the same physical device, these power converters.
yeah,
Um,
yeah,
but the difference is just how do you control them? And specifically, there are different paradigms for how do you decide what voltage and frequency to output onto the grid. And so grid following basically just says we're going to copy what the grid is already doing. So this is really a question of software, essentially. I mean, there's some
that's
hardware components that change if
that's
you're doing
exactly.
different
Mhm.
parts, but it's not like, we have to like design fundamentally new types of electronics. It's
Right.
not really a hardware problem at its core, it's a control problem. Um, and so that's what I'm working on is trying to understand, okay, for these grid forming controls, I mean, basically in my work, we've found that if you want to do these decentralized conditions that don't require huge amounts of individual analysis based on the specific parameters of your system, you really just don't want to use grid following control at all because it's very hard to get guarantees about when your grid following control will be stable or not stable.
Yeah,
Uh,
yeah,
but then the question is with these grid forming controls, how do you ensure that your grid forming controls will behave nicely with each other if they're using different types of controls? Yeah.
gotcha. We've had as speakers in our forum people from organizations called, for example, ISO New England. It's the
Mm.
Independent Systems Operators, and there are equivalents all over the country. Do you and your colleagues at Wisconsin, do you have interaction with the ISO equivalent of ISO New England? Because they obviously should be very interested in this.
Yeah, there definitely are ISO representatives that like so for us it's MISO, Midwest Independent System Operator.
Yeah.
Um,
Yeah.
yeah, I mean there are ISOs are definitely involved with this. I don't have direct connection with them in my research as of right now, but like, we have representatives from these people who come or from these organizations who come to our conferences and talk to us about things. One actually interesting case I'll just mention. So there's this consortium called Unify, which is working on specifically grid forming control, and trying to develop this. This is a collaboration between several different universities, several different industry groups, and several different like system operator groups. Um, and I mentioned Kauai earlier because at one of these meet conferences with Unify, we had the Kauai system operator or utility, Kauai utility, come and tell us about their system, which has been running almost entirely on renewable energy, like, by default running 100% renewable uh,
Sure.
for years now. Um, and part of the reason that have been able to do it is that they have an island that is not very big. And that means that if the grid goes down, it doesn't take very long to start it back up again. It just takes a couple hours. Versus if, the Eastern Interconnect has a blackout, it takes days to get power back up if it's a large scale blackout. So they're able to be a little bit more experimental in the technology that they put on their grid. Um, but yeah, you had the person from the utility come and talk to us about how they've deployed grid forming control on their system.
Right. I'm going to suggest that we stop screen sharing, but first, before you do that, if you could go back to the slide earlier in your presentation on harmonic phasors.
Yeah,
There was something in that I found intriguing. The current response that you show there seems to have a symmetric uh, as the wave change, the current wave dynamics change, you've got a seemingly symmetric response. What is that?
yeah,
What are the peaks and transients in that behavior?
that's a good question. So, I mean, I think the different peaks and transients, it's hard to say exactly because this is from a household that has like many different devices that are plugged in.
Yeah,
But in general, you often see with these power electronic loads that are trying to draw DC power from an AC system,
yeah,
is that they will pull. Okay, so I guess power is voltage times current for those who may not be familiar.
right.
And so here, when they're trying to draw positive power, and a
Yep.
constant positive power, essentially. And so what you'll see with these power electronic loads is
Yeah.
that when the voltage is low, they will try to draw negative power. Um, and when the voltage goes positive, they'll try to draw positive current. Or sorry, voltage is negative, they'll try to draw negative current. And voltage is positive, they'll try to draw positive.
I see. I
And
see.
that draws it const or that creates positive power. Of course,
Uh,
then you get like these like kind of bumps in the
yep.
power output, and then you have all sorts of filters and stuff in your converter that will try to smooth.
I see. So you need, in order to get the current, the power IV, you need the current to increase locally and in those transients or decrease depending on the nature of the transit. I get it.
Exactly.
Okay.
And the other thing is that's why we only looked at the odd harmonics. If you
Yeah.
notice, it went up 1, 3, 5.
Okay.
Because of the symmetry over the thing, you don't
Yeah, yeah.
get any even harmonics.
Got it.
You only get the odd ones.
Okay. Thank you. All right. We have some hands up. Let's end the screen share and we can go to Michael.
Hi, Dahlia. Thank you very much for your presentation. It's kind of got me wondering whether I'm on the right track here or not. So, in my business, I can convert biomass into oils and biogas. And the assumption is that this will be helpful to provide additional power to the massive amount of electricity we're going to be needing with electric vehicles, artificial intelligence. And so I kind of foresee where my systems can interact with the grid in some way, either as a microgrid or with net metering. But now that I see your presentation, I realize that the devil's in the details here. And am I on the wrong track here, or where
No,
do microgrids fit into the whole scheme of things?
no, microgrids are definitely a part of this. It's not something that I focus on in my work, but it's a big problem when you talk about grid resiliency. I know when you talk about, especially like, for example, this has been proposed a lot in response to wildfire risk, is that, okay, well, if you have a let's take California, for example. You have all of these big transmission lines that go through the mountains or through these forests to rural communities. And you often have high wildfire risk on those transmission lines. And so if you frequently have to cut off this transmission line, then that means that the community at the end of that line is losing power frequently. And so, in order to address issues of equity for rural communities, in order to address issues of reliability, what if you made it so that system could operate as a microgrid? And potentially it could either operate as a microgrid just when you need to cut off that power line, and then it can rejoin with the grid and act together in, synchronized for more reliable power. You also see microgrids are used a lot for indigenous communities that are remote. Um, for example, like there are communities in Alaska that are really far from the grid, and historically they've just relied on diesel-powered generators, which has all sorts of pollution issues, air quality issues, health issues. And so if you can rely on a microgrid that maybe doesn't rely on diesel generators, but has some combination of um, renewables and also maybe biochar or stuff like that, then that can help increase reliability.
But those generators still face the same issues that the grid itself faces. Is that correct? In synchronization, et cetera.
Yeah, so I mean, the thing is that it depends on the mix of generation that you're using. You can't have a system that relies only on grid following inverters. However, if you have some combination of, maybe let's say you have some, I don't know, uh, some generators that are not renewable or like use biochar or something like that. If you have some grid forming inverters, um, then that could be deployed. The other thing is also there do exist grid forming controls already. It's easier, don't quote me on this too much, but it does seem like an easier problem to experiment with a microgrid because the scale of the system is smaller and
Mhm.
it's easier to check whether it will be stable with some combination of controls versus a larger system where you have a big
I see.
utility serving hundreds of millions of customers and doesn't want to take too many risks.
Okay, thank you. Appreciate it.
Okay, Walter, you're muted,
Here.
kid.
The so Dahlia, having worked in on power generation, these turbines are huge machines, and I can understand how the concept here that when you change load, it really doesn't affect the frequency of 60 hertz, and I understand the concept now that when you have solar panels and a DC source, it becomes a problem. And so right now, I just checked to see what we're generating here in the ISO New England, and we're at about 40% solar power right now. And so I can see how this your research can help solve this problem, because as New England moves more towards renewable energy, let's say we get more batteries and more solar panels and everything, I can see how your research is going to help solve this problem. Is that correct?
Yeah. And the other thing to note is that when we talk about these ISOs, like the ISO will say like, okay, we have 40% renewable energy in the system. But it's also worth keeping in mind that electrically, ISO New England and ISO or MISO, Midwest ISO, those are the same system electrically speaking. Regulatorily speaking, they're different because they have different system operators controlling, which power plants come online and stuff like that. But electrically, the stability of New England and the stability of the Midwest are connected. And so I don't know what the overall percentage of renewables is on the total Eastern Interconnect of the US, which is the electrical system that includes all of these things. But it's also probably somewhat lower than just in New England.
Okay. Yep. In a follow-up question there, often several of us who follow the ISO New England, we see that when there's more than sufficient generation of electricity by solar or wind, it becomes a negative pricing. Now, I know you haven't addressed pricing, but what does negative pricing mean?
Yeah. So that's a really good question. A lot of also basically, yeah, it becomes negative pricing because basically the way the electricity markets work, specifically the real-time market, this is essentially the wholesale market, is that the generators will bid in to the market at whatever cost it takes for them to produce electricity. So for coal or natural gas, that's going to be the price of fuel. For like hydro will generally be around zero. Solar will generally be around zero because there's no fuel costs. Wind actually will bid in a negative number because you have a production tax credit on wind, where basically they get paid to produce energy based on government subsidies. And so because they get paid for every megawatt that they produce or every bit of power that they produce, it's actually a negative marginal cost for them because they make money by producing. And so that's why you'll see negative numbers. What that means is that for us, like as retail consumers, in general, unless you're in a deregulated market, but for people who buy power from the utility, usually you don't see that because the utility has kind of set pricing schemes that help protect us from these price fluctuations. And so basically we just get like an average cost essentially. But what it means for generators on the market is that basically that's a signal to them that, okay, there's too much power right now. And so they will get paid to stop producing power. Or, they will be losing money if they keep producing power at the same amount. And so that's an incentive for basically on these real-time electricity markets, the system operator to incentivize these producers to stop generating so much.
So the producers are the ones that are using a fuel, maybe, whereas wind power has power purchase agreement and at a certain price, but yet solar
So yeah, so
is
even
zero.
with these power purchase agreements, though, you have on these markets as long as the total power is getting met through various sources, that agreement is so people will have these power purchase agreements, but then they'll make other agreements on top of that where they'll start like buying power elsewhere or stuff to subsidize. But in general, by producers, I mean everyone though, because not everyone will have a power purchase agreement. Some will have the ability to control how much that they're generating. And so if the price is negative and you're able to control how much you're generating, you're going to stop producing power.
But the utility has to take the power from the wind generators and from the solar producers, right?
Yes.
They have to purchase it.
So I mean, I think part of the issue is also that there are long-term markets and then there are short-term markets. So I don't know exactly the details of how it works, but from my understanding, these power purchase agreements are on the long-term markets, but then on the short-term markets, you'll have other adjustments take place.
Good. Very good. Thank you.
Good. Albert.
Yeah, hi, Dahlia. I'm not a double E, and I was looking at all these conversions you're making. And my question is anybody trying to connect a direct DC link between the solar cell, which are producing DC, and the computer that use DC? Of course, you have to match the load, they need batteries, etc., and connect it to the grid. But anybody's considering that to avoid this double conversions that is not necessary and presumably inefficient?
Yes, that's a great question. The answer is yes, but generally only for microgrids. The issue is that our whole grid is built AC currently, and that's because back in the day of Nikola Tesla, you had to be able to convert your AC waves to high frequencies, and we didn't have these power electronics, these semiconductor transistors at the time. So the best way was to use AC power so that we could use transformers. But you're right, these days we can convert between different voltages in DC, which we weren't able to do before at any sort of decent efficiency. And so you have people who are saying, okay, well, if we're building microgrids, these small grids that are meant to run independently, why don't we just make them all DC to begin with? To avoid these extra conversion stages. The issue is that if you want to be able to connect your microgrid to the larger grid, which sometimes you don't, but sometimes you might want to, then you have to make sure that it can run in AC, either through one large converter or by synchronizing it, then you need to have AC. The other issue is just that we've built so much infrastructure and it takes so long to build infrastructure that is already AC that it doesn't seem feasible to actually change the whole scale grid to DC. But yeah, for newer systems that are self-contained, DC would make sense.
Yeah, actually, I was not thinking about a general microgrid, but rather just a power center. Like we hear now, they're going to consume so much energy and use solar, cover the whole roof, etc. So that may be even more controlled than a microgrid on a city or a town that ultimately has microwave and other things that need AC. But
yeah, I mean, that's true. The issue is that these data centers, at least, they want as reliable power as they can get. And, sure, you could put a solar system with a giant battery system, but realistically, most likely that's not going to be as reliable as the power from the grid itself, because you have all of these different this big diversity of generation sources that can help supplement each other when for example, the solar power might be low. The issue, of course, then is that the data centers themselves hurt the reliability of the overall grid, but that's a separate problem.
thank you.
Eddie.
Yeah, actually, it kind of segues into what I was going to ask, which essentially the nature of instabilities on the grid. Have they changed as a consequence of changing technologies? For example, data centers, it used to be, mechanical drives. Now it's solid state drives. Light bulbs used to be an inductive instability source, whereas today we have solid state devices. And I worked for a while with EMC, and we looked at actually the stability of grids around the world using our machines actually to gather the data. And it was rather startling how differences in countries, um, how different the stabilities were. Italy was particularly prone, for example, to instabilities, as was Saudi Arabia. I seem to recall. Anyway, that was the data from what we gathered. So I guess my question is, what do you know if the nature of instabilities is changing, particularly as a consequence of now we're getting AI and data centers. Data centers used to be at the intersection of two grids, so they had hopefully stable power. They could switch between the grids if they had to. Today, it seems more complicated. So I'm just wondering what your thoughts are on that.
Yeah, that's a good question. So I guess first I'll just talk about the data centers bit. Like, yes, the data centers I'd say the biggest obstacle for the data centers is that they are just the quantity of power that they are drawing. And that may not always be when we have enough power to give. So that's less a question of stability and more a question of supply and demand. The one advantage of data centers is that it doesn't matter where they're located. And so you do see companies building their data centers closer to sites where there is a lot of renewable generation. Um, and so that does allow some flexibility on the like locational front, which is different than other loads that can be helpful. But in terms of how the stability issues on the grid are changing, um, so I'll first, just for people who don't know about maybe these stability issues, like one of the biggest historical causes of these instabilities is you have long power lines where lots of power is being sent across a far distance. And that can create just kind of resonances where you'll start having power sloshing back and
Exactly.
forth. And so there are these modes that are like known. So for example, between California and Washington, there's a north-south mode because you have all of this hydro production in Washington state, and you have lots of people who live in California who consume power, and that can create oscillations. In terms of how those things are changing, one of the things is that this change from to lower inertia sources of generation. So this change from replacing, coal plants, for example, with renewable energy, that is changing the dynamics. And so some people have theorized that that might be increasing the frequency of these oscillations. Um, it could also be just changing where we have potential instabilities. And some places have observed oscillations that come from grid following inverters. So I think there was a case, I want to say it was in Florida, but I might be wrong actually, where there have been some like kind of noticed oscillations. I don't know of any that have actually caused blackouts, fortunately, but system operators have said, hey, wait, this is weird. We see this oscillation where we have lots of wind, for example. Um, and some, researchers have actually investigated these specific instances and been able to track down and say, oh, this was from this component in the grid following inverter interacting with other components on the grid. Um, and so that is a new type of oscillation or instability that we've seen crop up.
Mm.
And, at least in my work, it seems like that can be prevented by relying instead on grid forming control rather than grid following control.
Tom Hopper, you're muted, Tom.
I have a little question and a larger question. The little question, I think, is when I lived in Europe and phoned somebody in the US, there was always this delay in being able to get the other person to respond because of the distance. From western Nebraska to eastern Maine, there's also quite a stretch. Does that create any complications in synchronizing? How many microseconds is it?
That's a good question. So the answer is yes, but I don't know how many microseconds. There's also, I would say it's less the physical distance than the electrical distance that creates that um, time to synchronization. So specifically, if you have like the impedance of the wires between your different things, or your different points, that will create oscillations across that wire. And specifically, there are, it takes some amount of time to synchronize the system, especially when you look at very large systems, because of that. Um, and so one of the things that matters for the stability of the system, even in these like decentralized conditions that we're trying to develop, is it does matter the overall impedance of your system. Specifically, interestingly though, there's two ways that it matters. The first is that if you're the ratio of the most highly connected, like the least impedance node in your system versus the least highly connected, the one that's like way off in the middle of nowhere with a super long line. If the ratio between that is very like, those values are very different from each other, that will hurt the stability of your system because you have some places that are synchronizing very quickly and some that are synchronizing more slowly, and that can create some oscillations. Um, the other thing, interestingly, though, is that it's actually bad if if you have two generators that are very closely coupled together. And that can actually be a bigger obstacle to synchronization because essentially what you do is if you have two generators that are right next to each other, they might be fighting each other on how to stabilize the system. And that can create oscillations too. And so part of it is that you don't want things to be too far apart from each other, but also you really don't want things to be too close to each other either, at least for nodes that are trying to stabilize the system.
May I go ahead with my second question?
Yeah.
We have entered a period of cyber warfare, and the consequences can be, I would think, huge for the power grid because I think it's been said China and Russia and others know in detail how they can bring our grid down. In your area of research, do you know of people thinking about how to get microgrids stepping in if the grid is shut down to operate for local communities, and whether you can still power your house if the grid goes down? Of course, that seems easy to answer, but the microgrid question.
Yeah.
And do you know people looking into how to make our grid more secure?
Yeah. So yeah, those are, I guess, two questions. So yeah, there's the microgrid side of things, and then there's the cybersecurity side of things. So in general, yes, there are people working on both sides of this. For microgrids in general, just for any type of reason the grid might go down, whether that's a cybersecurity attack or an extreme weather event, people are working on how can you try to reboot specific microgrids. There's also some interesting work that my advisor in undergrad was working on called the Oakland Eco Block Project, which was essentially taking a city block in Oakland and trying to get it to operate as not only a microgrid, but a community-owned microgrid. So looking at different structures of community ownership, input, and making it more renewable. So that was an interesting project. But yes, people are working on microgrids as a form of grid resilience. The other question of cybersecurity is a big, like, growing area of research. So I know at Georgia Tech, for example, they're doing a lot of research on cybersecurity of grids, particularly since the Russia-Ukraine war started. And so they have done some work where they're like creating a model of the Ukrainian power grid to see like if they can detect vulnerabilities. And also they've done some work of modeling can you detect bad actors on a power system? Can you detect like, okay, is this person intentionally trying to destabilize the grid with the way that they use their power? I don't know the details of this work. I only know that they're looking at this at a high level. But yeah, cybersecurity is definitely a growing area of research.
Can I just say it's a delight to hear you talk and know so much in your second year.
I have very good mentors.
Albert, you have the last question.
Okay. Dahlia, you mentioned several wildfires that may be attributed to the cabling of the power companies. And some of these wildfires cost billions of dollars in damage, as well as so many people killed sometimes. My question is, does the utility, are they considering burying the cables, at least near areas that are susceptible to wildfires, like forests and stuff like that?
Yeah, actually, a lot of people in my research group, a lot of my colleagues are working on exactly that question. So you have there many people in at Wisconsin have worked on specifically creating a test system of California. It's not the actual grid because that is subject to a lot of privacy concerns, but they've created a scale model of the California, a simulation of the California grid, and they've also overlaid wildfire data on top of that grid to essentially determine how do we optimally decide which lines to underground. Now, you could say like, well, why don't we just underground everything? The issue is that is prohibitively expensive. It is really, really, really expensive to underground lines. So generally, this has to be an optimized decision of which lines have the highest risk, and use that to decide which lines to underground. But yeah, so it is a question of research. Generally, it's also there's some questions about fairness involved in that as well, of like, okay, is it just the communities that have more money that get their lines put underground and reduced? So this is fairness is also a big area of growing research when we talk about like infrastructure decisions or power shutoff decisions when it comes to power systems. But yes,
And access as well, whether
yes,
you have the ground to do it. Yeah. Thank you.
exactly.
All right, I lied. Michael has a final comment. Go ahead, Michael.
Just a quick one, Dahlia. We know that in the first current wars, Nikola Tesla beat Edison. Considering the changes today in technology, would Tesla still win a current war?
That's a good question. I don't know. I guess I would probably say probably not, or at least it would be much more of a battle. But it's important to recognize that we probably wouldn't have a power grid to the extent that we do, had Tesla not won that decision back in, the 1890s. But yeah.
Good point. Good point. Thank you so much.
All right, and look,
May I just say one word about that? If eventually power would be beamed down to Earth from some satellite, then perhaps we go back to Tesla.
Maybe, maybe.
I do want to give Dahlia a chance to get back to her work, but I want to make a couple of comments before I do that. Number one, Dahlia, I mentioned at the outset that one of my goals for the forum is to engage younger people in our conversations because your generation does represent the future of this country, not only in terms of power generation, but in terms of our direction. So this is important to me, and I think to the forum that we hear from people like yourself. And testimony to that point, today our resident historian, Vince Dixon, is off at East Boston High School teaching classes on civics. Let's see, what did he say? It's going to be civics, history, and technology. And I think that's a demonstration of just how seriously I think this whole matter is, and Vincent and I share that. We all share that. But I also want to say that it was incredibly reassuring to me to hear you talk today. And I mean this sincerely. You are the generation that will determine where we go as a country and as a planet. And energy and clean air and food. They're the basics of what we all require. And it's just reassuring to me to hear what you said because I'm gonna look. I wish you much good luck because I think we all depend on the kind of stuff you're doing. So I wish you much good luck and I thank you for being here. And I just want to turn to your grandparents for a moment to ask if they have any final comments for this wonderful granddaughter. Lita or Don? You're muted. You're muted, Lita.
Me.
No.
Okay. First of all, I want to thank you, Ron, for having Dahlia on, because up till now, we've only gotten to know a very sweet, very lovable, and obviously very smart kid, but we had no idea what she really knew. So I want to thank you for that. Dahlia, I think you have remarkable explication talent in terms of explaining the difficult in simple ways and in hearing people's questions and actually answering their questions, not what you want to talk about.
Yeah.
So congratulations on that.
I couldn't agree more. I think you're absolutely right. Dahlia, I hope you're setting a new standard for us in terms of getting young people to speak to us. So I thank you. We all thank you for being here. We're going to give you an opportunity to get back to your work at the university. And everyone have a great weekend. We'll see you again in 2 weeks. Next time, we're going to have a high school teacher talk with us.
I have to go.
She's from the Richmond, Virginia Public School System. It's Fairfax County Public School System. So we're going to continue on this theme for a little bit. And I just thank everybody for being present today. Enjoy the weekend. And Dahlia, thank you so much for being part of our group today. Take care. Bye.